Hello, everyone, and welcome back. We'll continue our journey on optimization. So, in the last class, we looked at nonlinear optimization, right? Constrained version, unconstrained version. We also covered some preliminaries in terms of what is a convex function, convex set, convex programming, which is popular, right? Today, we will focus on a couple of key algorithms that is important from a programming perspective, as in coding perspective, because as I mentioned last time, the computers cannot use analytical differentiation like human beings. Okay, we know how to calculate partial derivatives, Hessian matrix, and all that using analytical methods, right? It is possible to feed those rules to the computer, so it can also do those things, but it is not convenient. Okay, so computers use numerical techniques, numerical approximations. You know that derivatives can be calculated numerically also, right? By shocking the underlying variable a little bit and then measuring the change in the output and then taking the ratio. So those things can be done numerically. Okay, so computers can do that. How do we train the computer to perform optimization? Okay, using numerical techniques. And if so, we will look at machine learning techniques later in the context of finance. But the heart of optimization that is used in machine learning uses these couple of techniques that we'll discuss today. Of course, today we have much more sophisticated techniques that are available to us in the different packages. So more to come later, but today we'll cover the absolute basic idea of how to perform numerical optimization. Okay. All right. With that, let me get started. Okay. So the first and foremost algorithm that is extremely popular. This is what is used in all of machine learning. Because in machine learning, right, we are primarily trying to optimize or let's say minimize a loss function. So we'll see all those use cases later, right? But machine learning involves optimization, and that is what we are doing right now. So it uses an algorithm called as gradient descent. Gradient descent. Okay, so that's the algorithm that it uses to find the minima. Okay. All right. Now, for all intents and purposes, we'll assume that our objective function is differentiable and convex. Right? Because if it is not, then you have multiple local minimas and there are chances that you get stuck in local minima. We'll see that use case today also, but we choose objective functions which are convex so that there is one global minima, and then what this algorithm does is that it iteratively tries to converge to that minima. Okay, we'll start with a seed value or some guess value and then slowly steadily come down and converge at the minima. That's the idea. Now let's naturally think how we can develop that algorithm. Then I'll show you the algorithm and we'll do an look at the implementation in Excel. Obviously, all these are available in Python packages. You can just run them. You don't have to devise the algorithm or code this algorithm from scratch. These are all built in. Okay. All right. So before we go there, just trying to develop a natural understanding how we can find the global minimum. So given that you have a convex function is the shape of U-shaped, right? And here is the global minimum. This is where, um, let's call it, what should we call it? X star. So this is a two-dimensional graph. Same thing you can extend to higher dimensions, right? Let's consider everything in 2D. Today we are in 2D. There is a function y equal to f of x. We're trying to find out the minima, which is x star. At x star, the value of the function is, let's say, y star. This is the minima, okay, this point. How do we find that? So the idea is you start with a guess value. Okay. So let's say we start from here, x naught. Okay. That's our guess that minima exists at x0. Then what? How can we reach here? So the idea is at this particular point, you can obviously evaluate y0, right? If you are given x0, then y0 is just f of x0. So this point is known. This is given by the user. At this point, you have an idea of the slope. Okay. Uh, in fact, let me redraw this. It's too much straight. So we make it a little. Okay. This is my global minima, x, not x0, x star, y star. My initial guess is somewhere here, let's say, and that is x naught, y naught. Okay, so here I have an idea of the slope. Slope is given by dy by dx. At this point, x naught, y naught, which is my initial guess, is the slope positive or negative? Is the slope positive or negative as per the graph? I request you to switch off your cameras, please.
Positive, I mean.
Uh, Wait, I forgot to mute. One moment. Okay. Um, yeah, I'll probably need to edit that, please. Okay, that's fine. Let me rephrase. At this point, x0, y0, the slope is positive or negative? It's positive, yes. So if it's positive, that means positive slope means what? Positive slope means if I increase x, then y would increase or decrease? At this point, if I increase x, y would increase or decrease? Increase, correct? So this is my x, this is my y. We are trying to find minima, right? So we need to decrease y or increase y. As we want to find the minimum y possible, so we want to decrease y. We want to keep decreasing y until we cannot anymore, right? So if we want to decrease y, should I increase x or decrease x? I'm talking about x. If I want to decrease y at this point, should I decrease x or increase x? Decrease x, obviously. So I need to go in this direction. Okay, because slope is positive. So if I decrease x, then y will fall, right? So naturally, my initial, very naturally, I can write the next point is given as the current point minus dy by dx, let's say. So what this will do is, in the next iteration, it will update and we'll move to another point. Let's say we move here, x1, y1. I decreased x. I decreased x by how much? By this much. Okay, so I decreased x and then y obviously decreased. Y fell. Y fell from y0 to y1. All right. This is a positive quantity. So I take some positive quantity from x0. So x1 decreases and y1 would be less than y0. So I keep continuing this process until there is no further improvement in y. Because once you reach here, what is the slope? Slope at the minima, what is the slope? Slope is 0, right? So I can write the algorithm as xk plus 1. So k plus 1th iteration is given as previous value of x minus derivative of y. I can say probably at x equal to xk. That's my algorithm. Okay. Once I reach minima, the derivative would be 0 and x will not get updated anymore. I found the minimum. Okay. All right. I hope you understood this. Very basic infrastructure. Using the intelligence at that local point, that intelligence is the slope. Okay. I know in which direction I need to go. Okay. If slope is positive, decrease x. This works. Now, let's say that we are on the other side. Here somewhere. Our initial guess is here. Here, what is the slope? Slope is negative. Slope is negative. That means to decrease y, I need to decrease x or increase x? Increase x, exactly. So what should be my equation? X1 is equal to x0 minus, think about this, minus derivative or plus derivative? If I want to increase x and I know slope there is negative. Negative, negative, positive. Yes, exactly. So I still need to use the same equation, dy by dx. Because this is negative. So negative, negative will be positive, x1. So my next point will be, let's say here, x1, y1. X1 is greater than x0, but y false because of the negative slope. So there is one good thing I can see, that the same equation holds no matter what. Doesn't matter where your initial guess is, you can still always use this equation. Okay. So this is nice. And computers can calculate gradient numerically. Um, right? Computers can calculate. Sometimes you can also provide the gradient and the Hessian matrix if needed. First, you calculate, give the formula, and then computer will use it. All right. So this algorithm works. There is one small improvement we can do to this algorithm. What is that improvement? What is the drawback of using this formula as is? There is one improvement we can do. So this is, so my algorithm so far is this. Xk plus 1 is xk, right? Minus dy by dx. There is one improvement I can do. This is my step size. This is how much I will keep incrementing x, either in a positive direction or negative direction, doesn't matter. So the idea is, you should not leave everything to the raw slope. Okay, the raw slope may be too high or too less. I want to control that step size by introducing an additional parameter that I can specify. Some kind of uh, constant, okay? And this eta is called as learning rate. Learning rate. Eta controls the step size, okay? So basically, the slope will give me the direction, so that x will be either increased or decreased. Slope also has some value, okay? But that's a raw value. I don't want to use it as is. I want to control how much I want to increment x by introducing another additional parameter that I will choose. Okay, either 1 or 0.5 or 0.2, 0.001, whatever might be the case. And there are many reasons for doing that. Okay, the primary reason for doing this is sometimes if let's say the slope could be, let's say, uh, the slope is too big. Okay, for example, we have, let's say, this kind of a curve, and your initial guess is here, x0, y0, and here the slope is extremely a big positive number, right? Slope is a big, dy by dx is a big positive number, let's say, positive. Now, then in the next iteration, I'm supposed to decrease x, correct? X will decrease, y will fall because it is positive. If I use this raw equation, x1 is x0 minus dy by dx. This guy is a big positive number, let's say, possible. So what will happen is this new x1 will decrease so much that it is possible that you actually, let's say, come here, skipping the global minima. Okay, so the decrease is this much. Possible? The slope is too big and your increment is too big and you reduced x, but you reduced a bit too much. So what happened is you crossed the global minimum, went to the other side. Now your new point is here. All right. We don't want that. We don't want to skip the global minima. So if I reduce the step size by introducing another parameter eta here and choose a smaller learning rate, then it will not reduce so much. It will reduce by a little bit. Okay, so that's the idea, to have an additional control over the step size so that we don't end up skipping the global minima. We have this extra parameter called as learning rate. Okay, and while learning, I mean, you can call it because mostly it's used in machine learning, right? So yeah, that's the learning rate. So that's basically the algorithm. Okay, so our final algorithm is this: xk plus 1 is equal to xk minus some kind of learning rate and derivative of y at x equal to xk. Okay, now let's see this in action. All right. This is pretty much what I have written here, so you can read this, right? So the steps are like this. Start with an initial guess, x0. Evaluate the gradient. Gradient is a more general term. So in two dimensions, we have slope, but in higher dimensions, this will become gradient, okay? Evaluate the gradient at that point, which will give the direction of the descent. We are descending. Use a step size learning rate to descend along the gradient and move to the new point. Continue until there is no significant improvement in the objective function. So this is our infrastructure, okay? Right, so let's do one example. There are a lot of insights to it, so we can discuss. So our example is we want to minimize y equal to x square minus 2x. This is analytically solvable, okay? But this is just an example. We'll do it numerically. Analytically speaking, what is the minima of this, guys? Derivative, well, what is the minima? dy by dx equal to 2x minus 2. Where does it become 0? It becomes 0 at x equal to 1. Double derivative is 2. 2 is greater than 0. So we have a minima. At x equal to 1, the function attains minima. And what is the minimum value? Y min equal to 1 square minus 2 times 1, which is 1 minus 2, which is minus 1. So this is a parabola, okay? Same U-shaped curve attains minima at x equal to 1, and the minimum value is minus 1, okay? We'll solve this numerically using this idea. and there is a learning rate eta that we will specify. In our case, since the derivative is how much is the derivative? 2x minus 2. So we can plug in instead of dy by dx. In our case, it is 2x minus 2. Okay, this is our algorithm. Any questions before we look at the implementation? No questions? Okay, let's see. Let's go to implementation. Okay, so here is the animation for the gradient descent. We'll take a look at it, but let me walk you through the calculations. So this is our function x square minus 2x, derivative is 2x minus 2, and then here is the learning rate. For now, I have specified learning rate as 0.3. Okay, we can change it and see what happens. Initial guess is minus 20 for me. This is the plot, okay, plot of the function, and here we have minima. Minima is actually at 1 comma minus 1, right? That's what we derived. Yeah, x equal to 1, y is minus 1. That's the minimum. It's not at 0, okay? All right. My initial guess is minus 20, x equal to minus 20. At minus 20, value of y is how much? You can calculate. Minus 20 whole square is 400 plus 40, so 440. So this is my initial point. Okay. Now here is my algorithm. Initially, x equal to minus 20, correct? Y is 440. What is the derivative at this point? We know derivative is 2x minus 2. So 2 times minus 20 minus 2, which is minus 42. Minus 42 is the slope. You can see clearly at this point the slope is negative. So that is minus 42. It is actually a big number. Okay. My new x would be old x minus learning rate times the slope. Okay, learning rate is how much? 0.3. So this is my new x. From minus 20, I'm going to minus 7.4. That is what you see here. Minus 7.4, and the new y is 69.56. Y reduced, y fell, right, drastically. That is the whole scheme. From 440, y came down to 69.56. Again, find the derivative at this point. Derivative is 2x minus 2. 2 times minus 7.4 minus 2, which is minus 16.8. Again, the derivative is negative. So you increase x, it will automatically happen based on the formula. Old x minus learning rate 0.3 times slope, that will bring x to minus 2.66. And you keep on iterating. Okay, so this is the process. After some iterations, you can see it has converged. So my x has converged to 1. It's not changing anymore because the slope has become 0. If the slope has become 0, then x will not increment, right? And y is minus 1. So we have converged. After 100 iterations, the solution is 1 comma minus 1. That is exactly what it's supposed to be. Minima. Okay. Any questions so far? Is there any significance of y converging before x? What does that mean? Y converging before x. No, it's just a resolution. I think if I expand this, you can see, yes, yeah. This is just truncated. Cool. Any other question? It was rounded. That's all. Happy with the algorithm? Question from Celis: are there guidelines in selecting the learning rate? Absolutely. That's the elephant in the room. Okay, you brought up a very, very important question, and it's debatable. There is There is no strict rule actually. There is no silver bullet that will tell you, okay, this must be the learning rate. There is no such thing. Machines today are very, very intelligent. I mean, algorithms, they can figure out the right learning rate. So when you use a package, it's smart enough to choose the right learning rate. There are different thumb rules, but there is no exact science to choose the perfect learning rate. It's complicated. But let me ask you this. There's another question. Can you change the learning rate and it goes beyond? Yes, yes. We'll have fun. We'll play with this. That is exactly where I'm going right now. Let's do one thing. Let's change the initial value to a positive number, say 20. At x equal 20, the initial value of y was 360. All the slopes are positive. You see, all the slopes are positive, and x decreased, kept decreasing until we hit the minima. Make sense? You can choose another value if you want, 30. Right. So now you want to change the learning rate. Before we change the learning rate, tell me something. If I use a higher learning rate, or maybe let's do this. You use a lower learning rate. Let's choose a very low learning rate. What will happen? If I use a low learning rate, what will happen? What are the consequences of using a low learning rate? Number of iterations will increase. Perfect. Slow convergence. Excellent. It'll take a long time to converge. So all of you realize this, right? If we take a small step, then obviously take forever to reach the minima. That is the downside. What is the plus side? What is the benefit of using a low learning rate? Very low learning rate. Accuracy, not really. It's not accuracy. Uh, well, it is related to accuracy. The main advantage is the chances of skipping the minima is less because you are taking slow steps, very, very small steps. So when you reach, there is high chance that you will reach the minima the first time and then you will stay there. Okay, you will not overstep the minima. So that is the advantage. Okay, so let me know. So let's do this. Tell me a value. Give me a value, learning rate. I want a small learning rate. 0.00. Okay. After 100 iterations, I have 100, I think. Yeah. Wait, I'm checking this one, right? The minima that I'm looking at is, uh, yeah, after end of 100 iterations, this is the minima that I'm looking at, okay? I'm ending this algorithm after 100 iterations. Even after 100 iterations, it has not reached the minima. I'm here. Let me use another one. Point 0.1. Point 0.1 works nicely. I have reached the minima. It kind of converged. Yeah, still converging. No, sorry. Here. Yeah, kind of converged. So point 0.1 is good. Can we do bigger? What about 0.5? 0.5 actually converged in one shot, one step. Super fast. We got lucky. It's still too big. It took a huge step because 0.5 times this slope is 58. And then, yeah. If yeah, let's 0.65, what will happen? So this is a case where it overstepped. From 30, it went to minus 7.7, and then it came back, oscillated, and then came back. Right? If we use bigger, what is happening here? It's a perfectly symmetric shape, right? Around the minima, whatever it is. And if one learning rate means you're using this raw slope as is. Whatever is du by dx, just decrease x by that. So from 30, you went to minus 28. And then at minus 28, the slope is at minus 58. So you came back to the original spot, 30. So you're just bouncing. Exactly. You're just bouncing left, right. You will never converge to the minima. What if I use 0.9? It converges, but it oversteps the minima all the time, just back and forth. Okay, huge steps around the minima, but it converges. Did you get the feel of how it works? 0.98, right? It's not a, probably the ideal would be something somewhere around 0.3, I would say. Fast enough and doesn't overstep. So that's the role of learning rate. Any questions? Any other experiment you would like to do? Happy with this? Should we use a negative learning rate? No, if we use negative learning rate, what will happen? It defeats that entire equation, right? Because it's supposed to be minus dy by dx, but if you're multiplying negative, it does the opposite. So instead of going to minima, you're just, running away from minima. I have not tried it, but let's see what happens. Yeah, it just leaves the curve. Okay, all right. So we are good with this. Let's move on. This is the couple of extremes that I put in the slide, so you can refer to it. So if you are using a high learning rate, the steps would be bigger. That might work in favor of you or against you. If you use a learning rate, you're almost guaranteed low learning rate, then you are guaranteed to reach the global minima. This is a convex function, but it might take a longer time. Okay. So here is the thing. The issue with this algorithm is you should always use a convex function. If it is not convex, for example, if we have something like this is my equation, y equal to x4 plus 2x cubed minus 12x squared minus 2x plus 6. The derivative of this is, you can differentiate, right? 4x cubed plus 6x squared minus 24x minus 2. It has two minimas. There is one global minima here, but multiple local minimas. Now, this is purely luck based, but today the built-in algorithms in Python are so smart. They can handle these things very easily. So what you see here is, if you choose, your initial guess might be unfortunate, unlucky, and your iterations converge at a local minima, which is not global minima. So that's why we don't normally choose functions like this as an objective function. We try to avoid this scenario, so we only choose convex functions. So this is to show you that my initial guess is at 3, and it is stuck at a local minima. It's not understanding that it needs to go here. But if I choose, let's say, a good point, maybe -5, then it finds the global minima. Okay, starting with -5. And if you use a higher learning rate, okay, it still finds it. 0.3, this is too big. 0.4. We got lucky. Yep, this is what I was trying to replicate. Anyways, so this, ideally, we should not have functions like this in our objective function. Even if we do, algorithms today are smart enough to figure out this objective. Okay. Don't try this in Excel because Excel is, when it comes to optimization, Excel is very notorious. Okay. All right. So this is one issue we should try to avoid by choosing a convex objective function. Next, so this gradient descent, we actually use the slope because we are working in 2D. In multivariate problem, when the objective function has multiple input variables, then we can use the same idea. The only thing that you need to change is instead of slope, use the gradient. Okay, x is a vector. So your initial guess would be all those x's. You'll have some initial guess for all the different x1, x2, x3, x4, how many variables you have. Use the gradient of the z is the objective function, and use the same algorithm. So new vector is old vector minus eta times the gradient. Okay. But here, one important aspect that you have to remember is you need to update the new point simultaneously. So all the updates will happen in one shot. Do not update one x and then reuse the new x to update another x. Okay. How many variables you have, x1, x2, x3 up to xn, all of those get updated simultaneously. Old point minus eta times gradient, whatever it is, it's one shot update. Okay. Do not update sequentially is what I'm saying. That will be wrong. Do not update sequentially. It is simultaneous. All right. So let's look at an example. Okay. So this is going to be fun. Gradient descent in 2D. I have. Okay. There is one powerful result which we did not discuss fully because we're going too much into uh, geometry, algebra, calculus, which is probably not needed for quant finance. I'm just giving you the bare minimum infrastructure so that you can uh, relate to stuff when we do the actual use cases. So the one theorem that we have is that gradient vector gradient vector at a particular point is perpendicular to the level curve at that point. The gradient vector at any point, okay, is perpendicular to the contour to the level curve at that point. So right, actually we did an example using a circle, if you remember, but that's true in general. Okay, so here let's look at the gradient descent in 2D. This is our function z equal to f of xy, x square plus 2y square. Okay, and the surface looks like this. This is the plot of x square plus 2y square. Where is the minimum, guys? Minima, it's very easy to see without doing any maths, anything. Where is the minima of this function, guys? Guys, are you with me? Can you hear me? Okay, 0, 0. Excellent. Because these are squares. So square, the minimum value of a square is 0. So minima is at 0, 0, and the value is 0. Let's say my initial guess is minus 5, comma 5. This is my point. Okay, my initial guess. At this point, I need to find out the gradient. What is the gradient of this? 2x and 4y, correct? Yes. So 2x is minus 10, 4y is 20, based on the current point. So my updated x would be, updated point would be, there is a learning rate also, 0.1 here. Updated new location would be minus 5 minus 0.1 times minus 10, old x minus learning rate times fx, right? It's a vector update. And new y would be old y minus learning rate times Fy. So this is my new point. I came from -5, 5 to -4, 3. Graphically speaking, so I couldn't draw it here on the 3D plot, but I drew it on the contour plot. So you can see the action. In Python, I can probably plot it here in the 3D spot. So, so let's say we are here somewhere, okay? And based on this gradient vector, we will descend and we come to this new point. This if you project that entire behavior on the XY plane, it looks like this on the right hand side. So we have this point. This point is, wait, -5, 5. Okay. The next point is that where we are heading is -4, 3. Now this point would be on a level curve. -5, 5 would be on a particular level curve, right? And the height there would be, you can calculate the height, -5 square plus 2 times 5 square, whatever that is. This entire level curve shares the same height. The direction of movement is perpendicular to the level curve. So you can see the 90-degree, you can feel it. It's almost perpendicular, right? That's a theorem. So direction of the gradient would be perpendicular to the level curve. So this is our new point. Let's proceed. So if I go iterate again, I get the new point. So from -4, 3, right? Calculate the gradient, update. It's a simultaneous update of x and y, okay? We don't do it sequentially. We come down to -3.2 and 1.8. And that is where this is the new level curve, and that's the point. All right. You keep continue doing that. I think, wait, hold on. Do I have it? Actually, let me 1 second. Mm, this animation is not supposed to be like this. Or maybe it is lagging or something. I don't know. It's supposed to be continuous, but for some reason, uh, let me restart this one more time. One moment. This. Okay. Yeah, here it comes. I just basically want to show the entire path. So we took this path and then we are going there, right? Every time it is perpendicular to the level curve, and we slowly and steadily approach the minima. Okay. Any questions? So this is gradient descent in 3 dimensions. Um, Same idea, you can extend for higher dimensions. And finally, we'll reach minima at some point. So minima is 0, 0. We are almost there. After some more iterations, you'll reach there. Okay. Now, any other experiment you want to do? We can choose a different point. Maybe we can choose what happens with 5, 5. Yeah, we start from here. Same idea, it will converge like that. So this is the top view, okay? Whatever is happening on the left-hand side, the top view is this. Now let's do one thing. Let's choose a different learning rate. Question 100, is this optimization that Excel performs when using solver? Yes, that is correct. When we use the solver GRG nonlinear, it actually uses gradient descent at the back end to find the solution. Okay, all right. What if I use a bigger learning rate, 0.5? The step size is bigger. What is happening here, guys? Infinite oscillation? Yes. It is bouncing on and off because we are using a huge step size. Same thing that we saw in the I mean, yeah, 2D, the same thing happening here because we are using a big learning rate. It might explode and come out also. If you use anything bigger than this, let's say 0.75, it's a mess. Okay. It's actually not converging, it is diverging. All right. And if you use a smaller step size, obviously it'll take uh, a lot longer. I don't know how many iterations I'm supporting, but yeah. All right. Any doubts? Clear? Can we move on? Okay. There is one more algorithm, extremely powerful. So one drawback of this, as some of you already pointed out, is the necessity to choose the appropriate learning rate. Okay. So there is another method. It's Newton's method. Newton is everywhere. And this is very, very elegant. So what this does is there is no learning rate here. You can still use a learning rate on top of what we have to have an additional control, but you don't need a learning rate. This is called adaptive learning. Okay. How this works is same stuff. So we start at a particular point, right? Then pretend that this function is a parabola. Okay. Quadratic equation. So you can see that at this point, I have fitted the best possible parabola possible. How can I do that? Using Taylor series. Okay. So at this point, x, y is f of x, right? The true y is given by the original function f of x, but I can approximate the original function using Taylor series up till the quadratic term. Okay. So you know this equation, right? If I disturb x a little bit by amount t, earlier we used delta x. Here delta x is t. Okay. Value of the function at x is f of x, no issues. What is the value of the function at f of x plus t? If you know the true function, then you need to put x plus t to get the actual value. But I'm approximating the value of the function using Taylor series. Old value plus delta x times first order derivative plus half delta x square times double derivative. This is Taylor series expansion till second order. Okay. T is delta x. So you can clearly see that exactly at x, both my approximation, which is on the right hand side is approximation, Taylor series approximation. Left hand side is the true one. Both of these exactly match at x. That means when t is 0. If you put t equals 0, you get right hand side also f of x, left hand side also f of x. They exactly match. You can see the orange point is the where they match. But if you move away from that x by an amount t, then there is some difference. Obviously, one is true, the blue one is the true one, the orange one is the approximation. So there is some divergence. Okay. What this algorithm does is pretend that this curve is a parabola, the orange one. If it is the orange one at a given point, we know the minima of the parabola analytically. Okay, the parabola is simple. It's just a U-shaped, quadratic function. You know how to calculate the minima. I know where the minima exist for the parabola. the approximate function. So let's go there. Let's go to that x where the parabola is at the minimum, and then continue this process. Okay. So at every point, we are fitting a parabola using Taylor series approximation up to second order. Find the minima analytically. That is something we can easily derive. I'll show you that where the minima is. Let's go to that x. So this is the new x. This is the original x. I came here. Again, fit a parabola. Do the same thing. So every time we are going to the minima of the fitted parabola, and that's how we iterate until we reach the minima of the true function. Because here, where the true minima is, if you fit a parabola also, both of the minima will coincide. Minima of the parabola will be same as minima of the original function. That's the idea. Okay, now the question is, how much should we, what is the value of t? How much should we shift x? Well, we should shift as much so that we reach the minima of the parabola. What is the minima of this function? For what value of t this right hand side attains a minima? You can easily calculate that using, let's differentiate this, put it equal to 0. If you differentiate, you get um, t equal to, so we are differentiating with respect to t because these are all defined. Okay, at that particular point x, slope is already calculated, double derivative is already calculated, t is variable. T is what we want to figure out, how much we need to shift x so that we reach the minima of the parabola. If you differentiate, you get f dash x, derivative of this with respect to t, and then 2t by t, 2 will get cancelled, we get t f double dash x, right? This is equal to 0. From here, we get t must be this guy. This is how much t needs to be. And that's it. So you shift x by that much. We are going to the new x plus t. And that is given as x minus this, because t is minus f dash x divided by f double dash x. This is my algorithm. Okay, my algorithm is x k plus 1 is xk minus f dash xk divided by f double dash xk. If you compare this with the plain vanilla gradient descent that we had, which is xk minus learning rate f dash x, correct? So this factor 1 by f double derivative of f at xk is playing the role of learning rate indirectly. If you compare the gradient descent algorithm, then the role of eta is being played by 1 divided by double derivative. And this is dynamic because at different x, you'll have a different double derivative, right? The value will keep getting updated. So in a way, we are using a dynamic or adaptive learning rate, which we don't have to specify. It doesn't have to be static. It'll be very elegant. Once you reach closer to the actual minima, the learning rate would slow down automatically. It will be less. It'll be less, okay? Because see, if you have a very steep slope, here the slope is constant, okay? If you start from here, the slope is constant. It's not changing as much. It's a steep slope. So the descent would be fast. Because what is the double derivative here? The double derivative would be close to 0 because the slope is not changing. Slope is not changing means double derivative would be close to 0. So 1 divided by 0 is infinity. I'm just exaggerating. So the step size would be huge initially. But once you approach minima, here the double derivative takes a significant value because there is curvature here. Slope goes from positive to 0 to negative, right? Around this minima. So there is this is gamma, if you guys are familiar with options. Right? So because slope changes drastically near the minima, the double derivative takes a substantial value. So 1 divided by that naturally slows you down. So the learning rate reduces. So you want to slow down when you're reaching minima. So this is extremely elegant. Okay. We can see the implementation. Yes, totally. So we are using an adaptive learning rate. This is not Newton raption. Newton raption is something we covered in the previous last week. That is a root finding problem. Here we are trying to find the minima. Okay, Newton raption does not. It uses the slope. Okay, we did that exercise. That's a root finding problem. This is we're trying to find the minima here. It's a little bit different. It's little similar, but it's not the same. Okay, please refer to the last lecture on Newton raption. So this is our recipe. It's very, very straightforward. Uh, okay. Now, before we look at the implementation, actually, this is the last slide for today. I wanted to keep it short. How do I had another slide on this? Oh, okay. We can extend this idea in multivariate dimension. How do we do that? The algorithm takes actually this form, right? Xk plus 1 is xk minus the derivative that we need to have and then double derivative in the denominator. In case of multivariate, we need to use gradients and Hessian matrices, right? This will become the gradient, and 1 divided by double derivative would be inverse of Hessian matrix, because Hessian is again collection of double derivatives, right? So our new vector xk plus 1 is old xk minus inverse of Hessian matrix, which is actually this part, times gradient of f. That's the algorithm. Okay, so here is a homework for you. You need to solve this. There's two bivariate problem. Just write down this equation for the Newton's method. Like, what would be the update equation? How do I update the vector xy? Xy at k plus 1 should be xy k minus something. You have to figure this out for this using this idea. Okay, that's your homework. So let's do one thing. Let's see Newton's method in action. Uh, did I do it here? Oh, this is not the one. This is this is already something we looked at. Right, Newton's method. So we'll take the first example, x square minus 2x is what we did, right? Here, x square minus 2x. Gradient descent only use the slope, right? No double derivative is required. And we achieved the minima, and we experimented a lot on this one using the learning rate. Here, there is no learning rate. So let's say the initial value is, initial x is 4. Z is 4 square minus 2 times 4, which is 8. Our equation is, what is our equation for this? X square minus 2x. Let's see. Sorry. If our function is f of x equal to x square minus 2x, you need to do this. F dash x is equal to 2x minus 2. F double dash x equal to 2. Our algorithm is xk plus 1 is equal to xk minus 1 by 2, 2x minus 2, 2xk minus 2. That's how you need to update. Okay. Let's do this. Not this one. Oh. So we have initial x at 4. The slope is 2x minus 2, which is 6, right? Double derivative is always 2. This is what we just calculated. New x is equal to old x minus derivative, first derivative divided by second derivative. That's it. So we got 1. And surprise, surprise, we reached the minima in one shot. This is the minima, remember, for x squared minus 2x. The minima is at 1 comma minus 1. We reached in one shot. What is the reason? Let's try a different, there is no learning rate. Let's try a different value. Let's say, I don't know, 24. The slope is, I mean, these all work so nicely together. I always reach the minima in one shot. For this example, what's the reason? Who can tell me? Think about it. It converges in one iteration. Any ideas why this happens? If you understood the algorithm, the derivation of the algorithm, then you can answer this. Fxx is a constant is the indirect reason why this happens. It's the indirect reason. What's the direct reason? The direct reason is how does this algorithm work? The shift in x basically takes us to the minima of the fitted parabola, right? But our function itself is a parabola. It's a quadratic function. So the fitted approximation to this function is this function itself. This is the best quadratic function that you can fit, which is the original function. Taylor series expansion up to quadratic term will give you exactly this, the same function, because this is quadratic and we are trying to find out the best quadratic function at every single point. That's the parabola itself. So our algorithm is designed in such a way that it will take you to the fitted parabola's minima, which is the original function's minima. That's why you reach the minima in one shot. I did not realize this. I took this example, then I saw why this is happening. Then I thought, okay, this is why it is. So this is just to, show you that it works. Ideally, you would apply it to all kinds of functions, right? So cubic functions, exponential functions, and what have you. And take the, in 2 dimensions, it's very easy to implement, but for the higher dimensions, right, it will be a little difficult because you have to keep calculating the Hessian matrix at the new point, take the inverse, find the gradient, do a matrix multiplication, then update the x. It can be done in Excel, but it will not be nice because like in every row, you have to maintain that new matrix. Keeping a matrix in a row is not nice. Okay, so this is a homework for you. Just write the equation that should suffice. Today, the algorithms that we use for machine learning, which use numerical optimization, are extremely, extremely advanced. They use all kinds of techniques to speed up the process. Okay. But this is the foundation. Gradient descent still remains the foundation of all of optimization routines in machine learning. Slowly and steadily, we'll uncover other algorithms, but with a particular use case in context, so it will be easier. That's all I had today. Any questions? Yes, there is batch gradient descent and stochastic gradient descent that we'll cover when we talk about machine learning algorithms. Typically using for neural networks, we use those algorithms because for neural networks, it's a dimension explosion. Okay. There are so many variables and transformation we do. So we need to, in order to speed up the process, we come up with these clever tricks, which is batch gradient descent and stochastic gradient descent. We'll cover that later. Mm. Another question, please comment on optimization, calibration, parameter estimation, root finding. Um, yeah, it's too early for that, but optimization, right? We are trying to minimize or maximize a function, any function. Okay. Calibration has to do with fitting model prices to market price data. What is the choice of parameters so that your model price matches the market price? Parameter estimation has nothing to do with, uh, see, the role of calibration specifically is to match the model price with the market price. Parameter estimation is fitting a model to data. That data is typically historical time series. It is not the market prices as of today. That is parameter estimation. So let's say you are trying to fit a Garch model or volatility model, or simply you're trying to figure out let's say the stock price returns follow normal distribution. You take historical time series of a particular stock, find out mu, find out sigma, using either OLS method or maximum likelihood estimation or Bayesian method. Those are parameter estimations. So it has to do with fitting your model to historical time series data. That's parameter estimation. And the main choice for that is maximum likelihood estimation. We'll talk about that. And then root finding problem is just you're given a function, where does it become zero? Not minima. If we are trying to find out where f of x equal to zero, that's root finding. This is root finding problem. All right. Uh, yeah, finding saber parameter is parameter estimation. See, they use it interchangeably, but it is normally you do a calibration. See, you calibrate the saber model or Hester model so that you can um, get the appropriate smile that you observe in the market right now, and that is able to produce market consistent prices. Okay, so you calibrate the model to prices. You can do parameter estimation, but then that will not be used for no arbitrage. Okay, whenever you use no arbitrage model to, let's say, come up with market consistent prices today, that's calibration. Okay, and let's say if you try to estimate Vasicek model's parameters, three parameters, k, theta, and uh, sigma, from historical time series data, that's parameter estimation. It has nothing to do with generating market consistent prices. Again, this is further down the road. Right now, maybe it will not make sense to most of you, but we'll get there. Offline, if you have any questions, you can reach out to me. We can discuss. All right. Any other question? Ridul, how do we go about from here since we are close to primer concept being covered? I am still figuring out what's the best way. I think we'll start portfolio optimization because that quite naturally fits into the stuff that we covered. Uh, yeah, so modern portfolio theory, Black Letterman, and how do we create portfolios with constraints that achieve a particular return target, risk, utility functions, all those things will come in. I might start that, or we can go into derivative pricing. So I'm trying to, again, this is an optimization problem for me. Okay, and all these concepts are interlinked together. So we learn these in the context of something that is useful, but all of these things are reusable. In every topic, you'll find that these concepts are being the math primer stuff that we are covering, right? It's used everywhere. Anything that you pick up, you'll find these concepts together. So that's the reason we're building this base. Okay, but before that, we should start Python. Python will be fast because it's just you're reusing something that is already built in. Somebody else developed it. All the theory, underlying theory, and everything we have covered. So it's just a matter of taking data, running the package, showing the output and interpreting the output. So it will be fast. It will not be slow. So maybe we'll start that first and then go into the individual modules, separate modules. Okay. Any other question, folks? All right then. That's all I had. I'll see you next week. Thank you. Bye bye.